In the previous 3 videos, we learned about basic functions or basic relations, so basic functions and relations. Then we went through the textbook section on transformations of graphs. We learned about transformations of graphs in detail. And then we also looked at how those same transformations are applied to an equation that's in a coordinate system other than the Cartesian coordinate system, so the polar coordinate system, where the concepts are exactly the same. You're just thinking about it shifting in the radial direction or the angular theta direction. And so then, as usual, next I was planning on doing a full example problem video on transformations of graphs. And so I started looking at, first, these steps for graphing multiple transformations of functions. I looked at this in more detail and started working example problems. And it really became clear to me that, in my opinion, the authors dropped the ball on how they taught this section on transformations of functions, graphs. In the video where we went through the textbook, I hinted at some of these ideas in that, for example, for a vertical shift, you added a constant to the back end of the function, but for a horizontal shift, you added or subtracted a constant directly to the x term. And it was a similar idea for scaling, in that the way the textbook taught it, to stretch in the y direction, you multiplied a constant term by the entire function, but to scale in the x, you multiplied the reciprocal of a term by each x value. But what we talked about was that in reality, all of the rules are exactly the same for each variable. If you want to shift in the x or y, just go directly to the x or y and add a constant to the variable. If you want to shift in the negative direction of that variable, subtract if you want to shift in the positive direction of that variable. If you want to scale about a certain variable axis, go to each one of those variables and multiply that variable by the reciprocal of the factor you want to scale by. So in my opinion, the way they were teaching it not only made it more confusing, but then it made it hard to generalize performing transformations on anything that wasn't a function in 2 dimensions. That's all that section of the textbook focused on. It was functions in 2 dimensions. If you tried to branch out to something that's not a function, like a relation, like the equation of a circle, or a function or relation with any number of dimensions, with any number of variables, the way they taught it, you were going to be confused branching out. And again, I talked about that in the video where we went through the textbook. But as I studied these steps and worked some problems myself, what I realized is that the confusion and the limitations goes even further. And what I found is that all I need to do is show you a couple of key ideas about how these transformations work. And then with that, you don't need to worry about any steps. You can go in any order you want. And in addition to that, you'll also have an extra tool in your toolbox for transforming the graph. You'll have an additional way you can think about flipping the graph about the x or y axis. And even more than that, after we've gone through these videos, all of the transformation methods apply to all types of equations. So any number of variables, functions or relations, and also even if it has multiple outputs. We talked about like a vector valued functions. You could have like a certain number of inputs and a certain number of outputs. It's universal across the board. No need to worry about steps, and you get an extra tool in your toolbox as far as you can reflect about an axis in 2 different ways. All right, so to illustrate all of this to you, let's start by going through an example that the textbook gave about why, if you don't use these steps, it could be problematic. So they used the function y is equal to the square root of x as an example. Okay, there is y is equal to the square root of x. So they said that the goal is to shift the graph and then reflect the graph about the y-axis. Okay, so there is the y is equal to the square root of x shifted to the left or to the right 3 units. Add 3 to the x term. Now, to reflect it, what we learned is that to reflect it about the y-axis, you put a minus in front of the x term, or each x, if there's multiple x terms or multiple y terms, each x or y term. Okay, like that. So there, the orange graph is square root of minus x plus 3. But the book points out that if you didn't do it in this order, if you didn't shift first and then reflect, what would happen is that you would get y is equal to the square root of minus x. And then from there you shift, so you get what? You get y is equal to minus, open parentheses, or y is equal to the square root of x, and then inside of that minus, open parentheses, x plus 3. And this is different from this. Let's take a look at the green graph. Actually, this graph, I'm shifting by 2, so let me change this. These should be a 2. So the book said that if you do it in the order where you reflect first and then shift, you don't get what you want. It says this is what you wanted. You wanted this, and if you go in the other direction, you get what you didn't want. But when I looked at this, personally, I was under the impression that whenever we were reflecting from the beginning, we were doing this, not this. This is actually what I wanted. And really, to me, I would say that you want potentially either one of these options. You want to be able to choose one or the other. All right, so let's take a look. What's the difference between these two? And in fact, let me add something else in. So the purple is y is equal to square root of minus x. And we went from, so these two directions. Okay, and so here's the main idea. Let's go in the direction that the book said was the supposedly correct direction. We first shifted. Okay, we shifted here. Now we want to reflect. In reality, we have two options here. We have two ways we can reflect this. We're going to reflect this about the y-axis. We want to reflect this about the y-axis, and we have two options. But it's the same idea if we were reflecting about the x-axis. We have two options. The first option is that we can reflect about an imaginary y-axis that shifted with the origin. So reflect to this. Or we can reflect about the original y-axis. We can pick. The book is saying that we only want to reflect about the original y-axis. To me, not necessarily. The entire time I thought we were reflecting about an imaginary new y-axis that shifted with the origin. Okay, when you're performing transformations, if you do something like a shift, I would recommend that, so if you start off with just an x, and then you went to x plus 2, put a parentheses around everything that you've added, just to keep track. And then when you're done with the transformations, you could remove all of the redundant parentheses. Okay, if you want to reflect about the original y-axis, just put a minus sign in front of each x term. But if you want to reflect about an imaginary shifted y-axis that shifted with the origin, then put a minus sign in front of the entire shifted x term. You can choose whichever one you want to do. Now, if we look at this direction here, we started with y is equal to the square root of x in black. We flipped about the y-axis, but there was only one option because we were on the original y-axis. If you're already on the original y or x-axis, then there's only one option to flip about that axis. So we got this purple graph, and then we shift that purple graph to the left 2 units, and you just replace x with x plus 2. But there's nothing wrong with that. That could be exactly what you wanted. It's personal preference. If you wanted to first, you're imagining your graph, square root of x, y is equal to square root of x. You first flip it about the y-axis, then shift it to the left 2 units. What's wrong with that? Or you could shift it first, then you're going to flip a graph that's not on the origin. If you're going to be flipping a graph that's not on the origin, then you can choose between how you're going to flip it. Okay, let's start from scratch again. I'll give you a good example here. So y is equal to square root of x. Now, again, the steps don't matter. The order of the steps don't matter. Right now, I could flip this about the x or y axis if I wanted to. But there's only one option because we're on both the x and the y axis. So you don't have two options here to flip about an imaginary shifted x or y axis. So if I wanted to flip about the x axis, I would put a minus sign in front of the y. I would get this. If I wanted to flip about the y axis, I would put a minus sign here and would get this. Now, from there, let's say I flipped about the y-axis. Now if I want to shift this in the x or y direction, just do like normal. If I want to shift this up in the y direction 5 units, minus, and then just you erase the y and put y, and then put minus 5 because you're going in the positive y direction. Okay, let's take a look at that graph. There you go. We flipped this, then we shifted it up. Or we could flip it, shift it up 5 units, and then also shift it to the right 3 units. There you go. Flipped it, shifted it up, and then shifted it to the right. All right, now let's shift it first. Let's first shift it to the right 5 units. So we'll go x, put x minus 5. Okay? From here, we can shift it again, or we can apply a rotation. We're not talking about any scaling yet, any stretching or shrinking. But now we have an additional option. As far as flipping about the x-axis, there's only one option. You flip about the original x-axis because we're on the original x-axis. But as far as flipping about the y-axis, we could flip about the original y-axis or the moved y-axis, the new imaginary y-axis. Let's go ahead and just shift it up 4 units. Then we'll come back to flipping here. So shifting it up 4 units, we come here and we get okay, so now we have the option, we have 4 different flipping options. Flipping about the original y or transformed y, or flipping about the original x or transformed x. Let's flip about the original x and the transformed y. So to do that, to flip about the transformed y, what do? We put the minus sign in front of the entire shifted term. We do this. Okay? Now to flip about the original x, we put the minus sign right next to the x. Or no, I'm sorry, wait. To flip about we want to flip about the transform y-axis. So what I said was we put the minus sign on the outside of the y. No, we want to put the minus sign on the outside of the x. You apply the transformation to the equation on the other variable that you're working with. So if we want to flip the equation about the x-axis, the original x-axis, to flip about an original variable, we put the minus sign next to the variable, but we do that to the y, right? This here, putting the minus sign right next to the variable, not on the outside of not in front of the fully shifted variable, this is shifting about the original axis, not the transformed axis. But we're doing this for the x-axis, right? Because we're doing this about the original x-axis. You get what I'm saying? Remember when we talked about the rules for flipping about an axis, you put the minus sign in front of the other variable. If you want to flip about the x-axis, you put the minus sign in front of the y variables. Well, if you want to flip about the original x-axis, then go to the y variable and put the minus sign right next to the y variable, not in front of the entire shifted term. And if you want to flip about the transformed y-axis, the imaginary moved y-axis, go to the x variable and put the minus sign outside of the entire shifted x variable, like the entire shifted x expression, x minus 5. And there you go. Here is the orange equation. We flipped about the original x-axis, and we flipped about the y-axis, the imaginary shifted y-axis. Okay, now later in the video, we're going to come to some more complicated equations like this and perform transformations, but I want to go through scaling next, or stretching or shrinking, and then we'll use all three types of transformations on more complicated equations. Okay, scaling, stretching or shrinking. We'll start with the square root of x. Okay, so there is the square root of x. Okay, so again, what I'm teaching you here is everything you need to know so that you don't need to follow any steps like this. All right, so from the textbook, what you know is that if you want to scale up about a certain axis direction, the x or y axis or z axis, it doesn't matter how many variables. What that means is that if you have a constant a, any number greater than 1, it doesn't have to be an integer, just any number greater than 1. You're scaling up, let's say, about in the x direction. So you have the original function. This is the function you're about to scale, so it doesn't have to be the basic function. It could be already shifted, flipped, whatever. But you have a shifted, flipped, whatever function, and you're about to then scale up that function. That shifted function, we'll just call it has points x and y. It's been shifted and transformed in however many ways. What you're doing then, if you're going to scale along the x direction, up along the x direction, or stretch along the x direction, you're taking that a and multiplying it by all the x values and not changing the y values. Now, let's say you're going to scale down along the y-axis, so you're going to shrink along the y-axis. Well, starting with x and y, x doesn't change, and you multiply each y value by 1 over a. Again, we're assuming a is positive and greater than 1. It could be negative. The idea is if this factor was negative, you're scaling it and also flipping it. If this was like this, then you would be scaling it down in the y direction and then flipping it about the x-axis as well. All right, now to make this happen, to scale down, to shrink along the y-axis, what do you do to the equation? Well, you come to the variable that you want to scale. So you come to y. It's not the opposite like with reflecting. You actually come to that variable you want to scale. But what is the opposite is if you want to scale the y down, you would multiply every single y variable. Here there's only one, but like for example, here you would come to just this y variable, but here you'd come to every single y variable, or every single z variable, every single w variable, however many variables there are, whatever, and you would multiply every one of those variables by the reciprocal of this factor. So you'd multiply, you'd do this. It's the opposite, right? It seems like looking at like here that you're scaling all the y's up, you're actually scaling all the y's down by a factor of 1 over a, assuming a is greater than 1. And for this scenario, scaling up along the x, you would come here and multiply this by 1 over a, the reciprocal of a. Multiply the x values. That's the idea. And just a quick note, let's say we're starting with xy, we're starting with a shifted and transformed, it doesn't have to be this, it doesn't have to be the basic form, it could be any transformed graph. If we're coming from here and we're shifting it doing a rigid shift in the x direction, we're changing that to x plus or minus a y. Or if we're shifting it in the y direction, that's what we're doing to every single point on that graph, on that transformed or non-transformed graph. And if we are flipping it about the y-axis, we're doing this. If we're flipping it about the x-axis, we're doing this. And we talked about why, I gave examples of why it's the opposite like that. You can logically go draw a graph and then do this. Make every x point minus, you're flipping it about the y direction. That's exactly what you're doing, the y-axis. Okay, but here's what you need to understand so that you don't have to follow any order of steps. You can scale y is equal to the square root of x here. You can stretch it, shrink it along the x or y direction. Here, this graph is at the origin. You could also scale a shifted form of this. That's out here. or maybe it's been shifted and flipped. It can be anywhere on the graph. It doesn't matter. You can scale it along the X or Y direction. But if you use the method that's shown in the book, where you just come to the variable and put the necessary factor right behind the variable, what also happens is if the origin has been shifted, then the origin coordinates are also scaled. And you might think, well, wouldn't that also mean though, so if I scaled this unshifted graph by up 3 in the Y direction and then divided by 2 in the X direction. So I scaled up by 3, a factor of 3 in the Y direction, down by a factor of 2 in the X direction. And I applied that here. And then I applied that same scalar, I scaled this transformed graph, or this is just shifted. This is only shifted. So we haven't changed the shape here. This purely shifted graph, I scaled that up by 3 units in the Y direction, by a factor of 3 in the Y direction, and by a factor of 2 in the X direction. Wouldn't I have 2 different shapes? Why is that? Because look, I've got different Y values here and different X values here than I have here. You know, this XY value, if I come to that same point on the graph over here, that's a different XY value. The answer is no. If you went to each X variable for this graph and multiplied it by, what was it? It would be, we said, multiplied by 2, because you're scaling it down by a factor of 2, and you multiplied each Y variable by 1 over 3, and did that exact same thing for this shifted graph, the only difference would be that they would be, the origin point which would be different. That's it. You would have the exact same scaled graph, but with different starting points. Okay, well, that's good to know, but in my opinion, the way I was looking at it was that what I want to do is I want to be able to transform a graph, so shift it off the origin, flip it, do whatever, and then I want to have the option, I want to be able to scale it, but I don't want to move that point. You could absolutely just start at the origin, then scale it, and since you're at 0, 0, the origin doesn't move, and then apply all of the shifts and reflections you want, that would be fine. You could do everything you need to do that way. The only issue with that is that you have to follow those steps. You have to remember that you have to do all of your scaling starting at the origin. But if we want to eliminate any steps, it would be nice to be able to have the graph shifted off the origin and then scale it just without moving the origin. We can do that, no problem. So let's shift this 3 units to the right and 4 units up. Okay, so we started with the square root of x, and we shifted 4 units up and 3 units to the right. Now I want to scale this down by a factor of 2 along the x direction and up by a factor of 3 along the y direction, but I don't want to move the origin point. Again, if I wanted to scale it, but then also didn't mind applying that same multiplications to the origin point, what I would do is I would just come to, so we said up a factor of 3 along the y direction, I would do this, and then down a factor, no, it was, yeah, up a factor of 3 along the y direction, and then down a factor of 2 along the x. So then the origin, what would happen is the origin point would go from 4 times 3, would go up 12, and then to the left, 3 divided by 2. It would go not up 12, it would go from y coordinate 4 to y coordinate 12, and then from y coordinate 3 or from x coordinate 3 to x coordinate 3 divided by 2. It would be up here. And it would have a new shape as well. It would have that stretched and shrunk shape, stretched about the y, shrunk about the x. But what we're going to do here is we're going to get that exact same shape, that exact same stretched about the y, a factor of 3, shrunk a factor of 2 about the x, but without moving the origin point. How do we do that? What we do is we put the factor So we want to stretch about the y a factor of 3. So 1/3, the reciprocal of 3, because we're multiplying by a factor of 3, and just put it on the outside like we did for, wait, let me get rid of, there we go. Okay, yeah. And just put the 1/3 on the outside, similar to how we did with the reflecting. When we put the minus sign on the outside, we put the 1/3 on the outside of the shifted y. And then we put the 2, we want to shrink by a factor of 2 along the x, on the outside of the shifted x term. And there you go. See, it's really vertical because you're shrinking about the x. So it's pulling it in and pulling it up. When you shrink about the x, it looks like that can look like a stretch about the y, even though it's not, because you pulled it in. You've gone from here and you started here and you pulled it in, the blue in, and you also yanked it up. And that's it. If you wanted to flip this green graph about the transformed x or y or original x or y, same procedure. Come here, and if you want to flip about the original x, do this. The original y, do this. If you want to flip about the transformed x, do this. The transformed y, do this. If you want to shift this graph again, like a rigid shift, you're just changing this to something else. If you want to shift this up or down 2 units, then you would change this to y minus 2. Okay, and this is great because, again, you have no order. You don't have to go in any order. But furthermore, these exact same rules apply to, no matter how complicated the equation is, a function, here's a function, or just a relation that's not a function or relation in more than 2 variables, however many variables. But it could also be like, instead of just like if you have like 5 inputs and 1 output, instead of just having 1 output each time, it could be like a vector valued function where you've got multiple inputs and potentially multiple outputs. All you do, though, once you get past 3 dimensions, you can't conceptualize anything in past 3 dimensions, but you still just think about, like, if you've got like X, Y, Z, L, W, and you want to shift along the W direction, you just imagine, or transform, you just imagine a 5th dimension that you're shifting along. You abstractly think about that, even though you can't conceptualize a 5th dimension. We don't have any, we can't do that really. Or you're abstractly thinking about stretching along that 5th dimension. You're going to have an equation with 5, 6, 7 variables, whatever. Everything we just talked about in this video, if you want to stretch along that variable, you just go to each one of you have to apply that to each one of the variables. Let's do a couple of examples here. So I'm just going to write out some transformations. I don't have to think about the order or anything. I'm just going to write out whatever comes to my mind. So reflect about the x. Well, I guess it depends on if we've shifted yet. Let me just I'll make up some transformations as we go. Let's first shift in the y direction, the negative y direction, 3 units. And also shift in the positive x direction 2 units. So that's the negative y direction. And then the positive x direction. Okay, so we've shifted. Now let's scale this up by a factor of 4 in the y direction. But we don't want to apply that scaling to the origin point. So scale it up by a factor of 4. So we multiply 1/4 to the front of this y plus 3. 1/4 here. So Done. Now I want to flip the graph about the shifted y-axis. If I wanted to flip the graph about the original y-axis, I would just do this. But I want to flip it about the y-axis that you can imagine has been shifted with the origin. So I need to do this. Now this is kind of confusing, like, okay, what do I do here? Do I do this? No, that's wrong. You're doing this. You're taking, instead of doing this, you're doing this. So if you don't want so many parentheses, what you could do is, so you see it's minus x minus 2, that's minus x plus 2, right? So you could do this. You could do like that. So that would be, so you have minus x . There you go. All right, here's this, that was for a function. Let's transform a relation. All right, let's start off by flipping this about the y-axis. So we come to every x variable and put a minus sign in front of it because we're already on the original x-axis and the original y-axis. So there's no, we don't have to, we only have one option, just to flip about the original. So we just come to when we want to flip about the y-axis. So we go to each x variable and put the original y-axis. So we go to each x variable and put a minus sign in front of it. Okay, now let's scale down about the y-axis by a factor of 2. So we go to each y variable and multiply it by the reciprocal of 1 over 2, which is 2. Okay, now let's shift along the positive x-axis 3 units and negative y-axis 2 units. All right, so this is a little confusing. Pay attention here. So we're going to shift. So what you do here is, it's the same rule that you would use for any situation that we've learned even before this video for a shift. You go to the variable. We want to shift, I think I said, in the positive x direction by 3. You erase that variable. Put a parentheses and put x minus 3. In other words, we've only changed the way we do things for flipping, depending on if you are flipping about the original or the moved axis, and we've changed up scaling a little bit depending if you want to not touch the origin or you're okay with scaling the origin. That's the only thing we've changed. When it comes to actually shifting, translating, there's no difference. You just go to that variable, erase it, put a parentheses, and put x plus whatever, or y plus or minus whatever. So I put this minus sign here, I erase the x, and then I put x minus 3. Done. I come here. Don't worry about this 2 in front of the y. Just erase the y and put, we said, and the 2 in the negative y. Done. Okay? 2 minus sign. There you go. And I'll try and do a few more examples of this in the example problem video next.